Well, hey everybody. This is a piece mostly pertains to the LS project and swapping in a new engine. And as I was going at this and starting to look at things like mounting systems and engine mounts and transmission connections, I thought it might be helpful to point out some of the differences between the old gen engines and the new gen engines and transmissions even. Because I was involved in this back in the day. Back in the 80s, I had a small engineering team doing development and validation work. And we got pulled into a problem session. It turned into a project that, went a long time, a year or two. The essence of the story is that if you go back to the 1950s, 60s, and so forth, if you go back to, say, first-gen small block Chevy built in the 50s, its automatic transmission was a power glide, which was a fairly short transmission. The whole system worked pretty well. In the 70s, right, pickup trucks, for example, were typically a standard cab, 8-foot bed, or maybe a 6.5-foot short bed, right? On occasion, there was a crew cab, but that was kind of where they were. Now, fast forward into the mid-80s, right? Trucks are starting to grow. You had more crew cabs, you had more extended wheelbase trucks, pickups. Transmissions were getting bigger because we went to not only 3 speeds from the power glide, but we went to 4-speed overdrives like 4L60, 204R, which grew, got longer and longer. And then with the overdrive gear in a lot of cases allows you to run a little lower final drive ratio, which says, that's okay. But then you're changing the speed of the prop shaft down because the gear and the axle going from the road to the prop shaft is running at a higher average speed. It's running faster more often because the overdrive's keeping the engine speed down. By the end of the 1980s, it was pretty obvious that there were some issues. And I didn't redesign the engine, I didn't redesign the transmission, but my engineering team was working with the vehicle folks trying to understand how to make engine and transmission system at a system level to make it better. And the upshot of that was changes that ended up in the LS engine, the V8, the new small block, and then changes to the transmission. And I'm going to walk through those and kind of explain where that came from and why it matters to us. You can go way back, but I'll go to my 85 Camaro, and when I needed to go shop for a block, here was the mid-80s cylinder block. And if you look down here at the bottom, you can see the bottom edge of the cylinder block, and there's the bottom of the main bearing cap, rear main, and it just goes all the way across like this. And if you look at it from the side view down low, this is the bottom of the block all the way across, and you see the main bearing caps hanging down. There's kind of another view here. You get a little better look at that. If you take that engine and flip it upside down after my engine shop got done cleaning it up and putting it together for me, you can see here's the pan rail and the main bearing caps where they seat. So basically, that whole bottom surface of the engine was pretty much machined off flat, and the main bearing caps and the crankshaft are, up above the pan rail, or if you flipped it over, down below the pan rail, right? And that limited the Bellhousing pattern on the back of the engine to the transmission. You couldn't have any fasteners that were down below the crankshaft level, because there wasn't anything to attach them to. Just one more view of that. But this was the standard small block Chevy as it existed from, 1955, all the way through. They were all built this way. And then your oil pan was stamped and had no structure to it. It just bolted to the pan rail here. And it was a pretty doggone good successful engine. Once again, just looking at that, how that bottom looks then, and then you can see here's where the bell pattern runs, there's not even a bolt here at the top on this one. There's a bolt here and a bolt here and a bolt there, and so the distance top to bottom is pretty short. And I'll show you why that matters in a minute. Then when we got the LS engine, the fruit of a lot of people's labors, I say I had a hand in it. I had, I'm not responsible for it, but it was a team effort. We had a team of engine, trans, and vehicle people trying to find the best way to do this. And they ended up with, the final design was a structural oil pan that bolted to the bottom of the engine. The engine got to have a deeper, I call it a deeper skirt, so that the main bearing caps were not sticking out anymore. And in fact, for the LS, you can see they have cross bolts coming through the side of the block, holding the main caps, in place better. So it's a better, stronger bottom end on the engine. And it wasn't just a small block Chevy. If I go look at the 307 Oldsmobile engine that came out of the Cadillac, it's very much a similar design. They attach the main bearing caps just a little differently. It's a short skirt block. It's not a deep skirt block. Now I could flip over to, there were deep skirt engines. If you go look at the 428 out of my Mustang, that has the sides of the block come down below the main caps, and the bell pattern comes down further. And that was, that was a pretty successful design also. But what happened during the 60s was there was a lot of work to do, I'm going to say cost and mass reduction, and take out a lot of the extra heavy cast iron. And engines through the 60s and 70s especially got, deep skirt blocks were kind of a rarity. I haven't gone and looked at all of them, but many of the engines, your oil pan rail was roughly at the center of the crankshaft. So you can see if you look at the bottom of the LS that, here's the pan rail, and you can see the main cap bolts and the main, you've got all this structure in here that's keeping the bottom end of the engine stiff, which is a great thing when you want to do high RPM and so forth, and it's one of the reasons probably that this engine is so successful. And if you look at the 204R that came out of the Cadillac, it's very similar. You can see off the Oldsmobile that I think this one is the dowel pin. And you can see there's a bolt there and there's a bolt here. And one of the things that Oldsmobile and Buick did, their pattern was different than the Chevrolet in that they had these two bolts way high up in the corners of their bell housing pattern, which meant that from top to bottom of the bell pattern was a little taller. And again, I haven't got to the punchline yet. This will make more sense in a minute. And today, what goes with the LS engine is the 4L60E or the 8-speed or the 10-speed. But the 4L60E was the first one. And they went to a separate bell housing that was almost a full circle. You had structure all the way down to the bottom. And it required so much more aluminum in the case that they had to go to a bolted design where the original 4L60 was a one-piece case. And you can see, here's the original Chevy bell pattern here, and this one actually used the top bolt off the truck. Some engines did and some engines didn't. So this is the original Chevy bell, and when you get down to here, you're basically at crankshaft level, center of the crankshaft. What was added was these two bolt holes at the bottom and this contact surface down here that basically gives it, instead of just having the height from this bolt to this bolt vertically, you now had strength all the way to the bottom. So if you want to see it in a cartoon, here's my cartoon. Original small block Chevy with the pan rail at the center of the crankshaft, and then the automatic transmission, lined right up on that, and there you go, right? And in fact, it shows this bell housing, but you know, this bell housing actually was generally cut off, like that 204R picture, and it just had a plastic cover on the bottom, which was really nice for servicing things and putting in flex plate bolts and stuff. It was, the access was nice. But there's something in this design called a beaming mode. And beaming, it has several different natural frequencies. The beaming mode is fairly complex because it isn't near as simple. That's why I'm going to call this a simple beam, and I'm going to show you, I got a hacksaw blade here, right? And engine and transmission together tend to want to do this. They tend to want to bend. Technically speaking, our simple beam isn't at the ends. It's got a support kind of here in the middle. And it flexes like this. So when you get a vibration load from, you hit a bump, right? And the engine and transmission bounce on the mounts, it tends to want to flex and bend. And you'll get a shape like that or like that. And it'll vibrate at a fairly high frequency. And I'll stop here for a second and I will show you, what this looks like. How does a hacksaw blade bend? Give me just a second. So in talking about beams, I've just got here as a hacksaw blade, just kind of do a simple demonstration. If you clamp it down to a solid surface like this, this one's got a pretty good flexible spring rate to it. If you push it and let it go, it springs, and it's got an oscillating frequency based on its stiffness, its length, and the dimensions where it's supported. And I'm showing it right now being supported at one end. I showed you some pictures with beams that are supported in the middle, and the beams supported in the middle are trying to flex like this. And then I'll show you in a minute here with some weight on the end that this changes the natural frequency of that beam. Now if I add a little bit of weight to my cantilevered beam here, got a screw and a nut on the end of it, and you flex it that way and let it go, you'll see that the natural frequency is lower than it was a few minutes ago. And as engineers work through different technical projects like bending of systems and beams, the mass and the spring rate and the damping are the things that are most critical to it. Okay, now that you've seen how that flexes, it's just kind of to give you an example of where I'm going with this. So now, this is kind of exaggerated, but if you looked at how the engine and transmission bend, they have a beaming mode. They want to do this. Like you can see in the picture, the engine and transmission want to bend, and then they want to bend back the opposite direction. And the engine's heavy, the transmission's heavy, and so they want to go back and forth. And the only thing that you have that resists that back and forth is the bell housing pattern. And then, to make it a little more fun, is we end up with these with kind of an overhung load, because we start adding in transfer cases on the four-wheel drive trucks, and you end up with the load of the prop shaft on the end of that. You have the beam with its intermediate supports, and it wants to flex. This is kind of what it looks like, engine and transmission with the prop shaft, and this is the prop shaft section. And then we added transfer cases. And in the 80s, you'll find again, as you went to extended cabs and long beds and so forth, some of these prop shafts got pretty long. And some of the trucks had a center bearing. They'd have a two-piece prop shaft. But those are expensive and complicated, and there was a lot of work that went on to try to get a single prop shaft. And you'll know, there were aluminum composite shafts in some of the trucks in that time frame. And then the prop shaft itself drives a bunch of the vibration. So, here's just a metal rod. I think this is actually out of my son's, one of his rocket kits, but neither here nor there. But if you say, that looks a lot like a prop shaft, when it spins, you can even see right here, it's not perfectly straight, so it's vibrating a little bit. Well, what happens is, and the reason for the dotted lines in my picture, is that the prop shaft tends to want to, first of all, have some imbalance. The second is that it's a tube. And as it goes faster and faster, it wants to start moving off center, and it whirls like this. And there's something for prop shafts called a critical speed, where you can turn a prop shaft fast enough that the weight will get so far out that it'll go boom and it'll just come right out of the car. It'll break. You can go to the textbooks and calculate it. It's a well-known phenomenon, and it adds to the vibration in the system. So you can see here in my picture, you can see the dotted line is kind of the prop shaft wanting to twirl. And then that puts more load in the back of the transfer case and or transmission, depending on whether it's a two-wheel or a four-wheel, which causes the engine and transmission to go back and want to bend again. So in the late 80s, and maybe even sooner than that, in the time when I was working with it, the mainstream method, and if you've got an 80s truck, or probably early 90s, if you've got one of these trucks, you may very well find that they have braces. And what they call pencil braces, and they had structure that would go from the engine pan rail down to someplace on the transmission. And they would have them from the top of the engine to back of the transmission, back of the transfer case. I saw some systems that had 4 or 5 braces on them. They had a system of braces trying to stiffen this up to keep it from wanting to bend. What tended to happen is you were developing a new vehicle and you didn't know how this was going to turn out until you got fairly well down the process. In other words, the vehicle's starting to get toward production, and you'd be tuning it with pencil braces. And there are 2 things you have to worry about. One is just noise, because all that vibration of things beaming, if it's not stiff, there's a noise and vibration characteristic that will put vibration into the cab or into the car, and noise and shock, various forms. And so you really want to get that to be a stiffer system if you can. So the 4L60 and the LS were being, the 4L60 already existed. The LS was being designed at that point. And I was part of the campaign to encourage looking at redesigns of both of these pieces. And so the LS went to the deeper skirted block, which you kind of can see by the extra little piece of material there. And then they designed an oil pan that was, instead of just being stamped steel, was die cast and structural. And the structural does 2 things. One is it helps the engine, because it helps keep the bottom end of the engine under control and rigid. And the more rigid you can make it, the better off you are. And then it gives you something to mount a full circle bell housing to off the transmission. And now you can start putting some fasteners down here, which make that engine transmission interface a whole lot stiffer. Here's a look. We were just test fitting that oil pan onto an LS, onto the 5.3. So the bolts aren't run yet. We just have that set up there. And this is not the original truck pan. This is a different pan because we needed a new pan that would clear the cross member. So you got a new pan, and you can see places where you can put in bolts here now to tie to the bell housing. And then again, if you come back and you look at the full circle bell, what goes along with the LS are these fasteners down at the bottom. So when you get to the end, and you get that engine and transmission bolted together, you now have better attaching points and connections down at the bottom. What I will tell you though is we did have a little bit of a challenge, and that is that the oil pan that we needed that fits the car, these bolt holes don't line up with the bell housing on the truck. I think one of them does and one of them doesn't. And so the first question is, well, okay, how critical is that? And we're going to take a hard look at that, but we will probably run without all the bolts down low. The original small block ran that way for years. We're putting this in a car. Axle ratio is not going to be too deep. And it'll still have contact. The bell housing will still have contact. It just may not have all the bolts. So it could separate perhaps, but you'll still have the benefit of the stiffness in one direction and a little less stiffness in the opposite direction. Something we're going to have to work on. I don't think it'll be a critical problem, but it's something to be aware of as you're planning. I'm not worried if we don't get all of the bolts in. I don't think it'll be critical for us. Knowing how this engine ran in the past, and the engine and transmission, and our car application, we're not going to put all the bolts in. But I'm going to look at it and see what we can do and how close we can get it. But that's kind of the backstory on why, as we're putting in a new engine and trans, why it looks so much different than the old ones. Well, hope that helps. That's all for now.